All right, welcome everybody. This is episode 45 of Games with Go, and today we are going to start doing some lighting. So far we have a little program where we can move around, rotate our camera around, and see our objects and put textures on them. But right now everything's just lit uniformly. There really is no lighting at all. So we're going to fix that. So when you're working with something low level like OpenGL, there is no built-in lighting. You can't just say gl.create light or anything. You have to do it all yourself. If you're using something like Unity 3D or Unreal Engine, they've got light and camera objects built in you can use, but we're going to learn how to do it ourselves. So let's start with the simplest kind of lighting, which is just ambient lighting. And ambient lighting just lights up everything in the world the same amount and by the same color. I'm going to change the width of our window to make it square so we could do some side-by-side editing with our shader, just so we have room on the screen. So just to show how easy ambient lighting is, I'm just going to do it in the shader. So we'll go ahead and start up our program. I'll move back a little bit, get it at a nice angle. Okay, let's move. Crap. Because of the way I've done mouse capture, I can't easily move it. There we go. All right. So I'm going to make a light. And a light will be defined just as a color. Call it ambient light. And we can make a new vec4 in GLSL shader language, just with the vec4 keyword. And let's make it a bright white light. 111 for RGB, bright white. So all it takes to apply a light to a color you already have is to multiply. Because the OpenGL colors range from 0 to 1, you can just multiply things together to sort of blend them. So let's do that. We'll say frag color, instead of just equaling the color you get from looking up the color in the texture, we'll multiply times the ambient light to get our final color. Now for now, that's going to look the same because we have a bright white light. But what if we change it to a red light? Now we see it lit like it's red. We go back to white, and now what if we want to say that it's pretty dark? If the ambient light's pretty dark, then we can go down to something like 0.3 for every value, which represents a white light, but it's dimmer. And then we see things get really dim. So that's the most basic kind of lighting, right? Ambient light is just this light that's everywhere, coming from every direction, so everything's lit the same. So you might ask, why is that useful? Because normally lights have some direction they're coming from, like up from the sun or from lights on the roof, which gets you, the shading you're used to seeing in 3D. So what's the purpose of ambient light? So aside from just being one way you can light things and not have to do any work, just so you can see them, it's also useful to simulate realistic lighting. So let me show you what I mean. So if you imagine a cube in some space, and imagine that there is a point light or spotlight, like right here, and it's sending rays of light out like that. So if this cube were floating in the complete darkness of space with nothing around it, the way it would be lit is this whole face would be lit up brightly, and all of the other faces would be completely dark because the light isn't hitting them. So if you implemented a directional light, the simplest way that you can, that's how it will work too in 3D. The light, you'll look at where the light is and where the face is, and if the light is hitting it at some angle, you light it up. If the light's not hitting it, it's completely dark. But if you imagine an object in like a room or some realistic environment, you might have walls all around, or trees or other objects. And so your point light is not just sending rays of light at your cube, but also at the walls and the ceiling and the floor and other things in the room. And some of that light bounces off. So some of the light bounces off the wall and hits the cube again. And some of that light's going to get to these faces and light them up a little bit, right? And so to do that math realistically is a lot of computation, because you're casting rays every which way, calculating how much of them bounces, where they bounce, then they bounce again and again. And you would do that for something like maybe if you're doing some really realistic rendering for a movie, and it would take, potentially minutes to render each frame, or even hours. Or you might do it to calculate light maps ahead of time, like the old Quake engines used to calculate light maps ahead of time, doing some of this reflection calculation, and it would take hours. So for real-time lighting, you don't want to do all this. And you can just approximate it. The net effect of all this bouncing is that everything just ends up a little bit lit, even if no light is directly hitting it. And so you can approximate it by just giving everything a small amount of ambient light. So if we go back to our two programs here, so you can just do something like this, give everything an ambient value of 0.1. It's too small to see probably on stream. We'll go back to 0.3. That way everything's got a little bit of light, even if a light is not hitting it. So it gets you a very easy to calculate. You're just doing one multiplication, approximation of what you call global illumination, right? Approximating all that light bouncing around. Okay, so that's pretty simple. So what we got to do next is actually do that directional light, so we can get shading, and you call that diffuse lighting. That process of calculating the light that is actually shining on things, and you calculate how direct that light is. So if the light's going straight on, it's brighter. If the light's kind of a glancing blow, it's darker. So we're going to do that next. And one of the things you need to do in order to do that is you need normals for all of your surfaces. So what is a normal? So a normal is just a direction perpendicular to the surface. So if you imagine a face of our cube pointed directly at us, the normal for that surface, for these two triangles, remember these are two triangles, is an arrow pointed straight at us. The right side of the cube that we're seeing edge on, the normal is directly to the right. For the left side, to the left. The top side, straight up. The bottom side, straight down. Right? So we want to calculate those normals for every vertex of every bit of our triangle. And we're going to use that direction to figure out how the light's going to react. Right? So if we have a light here, for instance, and it's hitting this side of the cube, we figure out between looking at this normal and the direction, the vector for the light, how bright it should be. Right? And we figure it out again for every face. And so to do that, we need to pass normal data onto our shader. Currently, we don't have any. All we have is the vertex, which we have as the first three things in our vertice list. Then we have these UV coordinates, and we need to keep those. So what we're going to do, we could just type them in by hand. Because it's a cube, it's pretty easy. There's just 6 different normals, one for each face. But because this is an instructional stream, and because typing those numbers would be boring, we're going to actually compute them instead. So maybe we should make a function in our GoGL library where we're given a vertex, it will compute, or given a set of 3 vertices, it will compute the normal to them. So let's do that. So we will take, let's see what we need here. Okay, yeah. So to calculate a normal to a surface, this is some OpenGL documentation on how to do that. And it's basically describing what you want to do. You get a vector by subtracting one vertex of a triangle from another, and then a second vector subtracting the third vertex from the first. And you get these normals by multiplying your vectors and subtracting by multiplying in the other direction and so on. And what they're really describing here is something called a cross product. This is how you do a cross product. This multiply and subtraction on a 3-dimensional vector. So we've got our MathGL library, and it's got cross product built in to its vector 3. So we don't even have to do that much code. We can just use its built-in cross product. So let's do that. Let's do a helper function, and we'll call it triangle normal. And we will take in 3 points to define our triangle, and those will be MGL vec3s, 3-dimensional vectors. And so to get the cross product, let's see. Okay, so first we need to do the subtraction to get our 2 vectors. So on here, first we need to get these vectors u and v. All right, so we'll take p2 minus p1 and p3 minus p1. And the order in which you do this decides which direction the normal goes. So if you imagine a 2-dimensional triangle in space, right? One side's normal is that way, and there's a normal on the other side too. And so you want to get the outside of our cube, not the inside. Just checking chat for questions real quick. All right. So let's do this. So we'll say u is equal to p2 minus p1, and v is equal to p3 minus p1. And then we want the cross product. So we'll say that our normal, we can just return, because we're going to return a vec3, which is the normal. Return u dot cross v. Right, so that one line there represents all of this. Right, that's the cross product. So that's pretty easy. Right, so now we have that handy. We'll probably, if you start doing more fun stuff with OpenGL, you'll probably use something like that again. Okay, so these are our vertices in UVs. And we're going to make a second array for our normals. So we'll say normals is equal to make float 32 make a float 32 slice, and it'll be 36 long because we have 36 vertices here. 1, 2, 3, 4, 5, 6 times 6. And then for, let's see, for I is equal to how should we do this? Let's do that. For IV is equal to range vertices. But really we want to go over these 1, 2, 3, 4, 5 at a time. What's the syntax for that? There is no syntax for it. You just do it the normal way. So I is equal to 0, I is less than 36, I plus plus. So we're going to iterate over each vertex. And calculate its normal. So the first normal is going to be, we need to make a vec3 out of the first 3 triangles. So I guess we actually want 6 times 2. Each one of these is 2 triangles. So really we're going to go from 12. I'll call this try to avoid confusion. Okay, so no, we'll do it face. So face, 6 faces. No, triangle. So P1 we calculate an index is try times 5, 15. Right, because we have a span of 15 values for each triangle. And P1 is equal to ngl.vec3 vertices index vertices index plus 1 vertices index plus 2. 2 is equal to ngl.3. Then we want to advance the index by 5 to get all the way to the end, to the next one. And then P2 can be the same thing. OpenGL 32. And then P3, same thing again. Then we can get our normal from GoGL. And we just pass P1, P2, P3, get back our normal. And then normals of, let's see, two, three. So we have actually 3 normals we're going to update, because for each triangle we put the normal on every single vertex. Right, so we go 1, 2, 3. So it's going to be triangle times 3 plus 1 plus 2. Regular equals. Oh. X, Y, Z. Does this make sense? Try times 9. So we've got 36 normals, but it's 3 floats per normal. So that should be 36 times 3. I think that is correct. So at this point, we should have normals filled up with the correct normals. Any questions so far, chat? Yeah, chat. Remembered that range does not have any the syntax I was trying to do. There's like languages like Rust and F# have like a syntax like that to go from 0 to 10. Okay, so now we have this separate buffer from this one, and we got to use it. So we are going to make another buffer. And it's a vertex. Is it a vertex array? It's an array. this is for the array buffer. All right, let's just try it and see what we get. So we need another vertex array. So we'll call it our, let's see if this works. Okay, so we're getting our normal data in there. We can do a third vertex attrib pointer. Size is 3, just like our vertices. Floats, just like our vertices. Not normalized. And the stride is just 3 times the size of a float and no pointer offset. I think this will work. Also, a question I have. Do I need this? Or is that left over from our element buffer array? Yes. Okay. I think I need to make a new buffer array. Yes. Okay. Yeah, okay. So our vertex array is going to know about all of this stuff, our one VAO. But we need to bind multiple buffers. We don't even need to keep that variable around, I don't think. So now we make a new array buffer. And then we unbind our vertex array. So I think this VAO will then know about all of this data. Yeah, I think that's good. Buffer 1, buffer 2. All under one vertex array. Okay, so now what? We have normals. We need to update our shaders a lot. to deal with all this stuff. So our current vertex shader, and remember this vertex shader is a program that runs on every vertex in our world. So we've currently got model view and projection, which lets us have our camera that we can move around. We're going to need to output a normal. All right, so every vertex has a normal. And just to remind you something about how the shader kind of pathway works, right? You have your triangle with 3 points. And when a vertex shader emits a value for a vertex, so say, let's just pretend we have some one-dimensional normal of 5, right? And a one-dimensional normal here of 1. When you get down to your fragment shader, remember your fragment shader runs on every single pixel inside this triangle. All right, say this was 2. Automatically what happens when your fragment shader asks, okay, what's the normal output from the vertex shader? It automatically interpolates, right? So a pixel down here is going to be some weighted average of 5, 2, and 1. So maybe it's 3. And a pixel up here is going to be 4.9, right? So by having a normal for each vertex, you can calculate the normals for everything. Now, in the case of normals, normally that's always going to be the same, right? Like it's always going to be 5, 5, and 5. So the interpolation's simple. But there are other things like you can give colors to vertices and it'll interpolate for you. So when you output something from a vertex shader to a fragment shader, just keep that in mind. That the fragment shader is going to get an interpolated value between the 3 points of your vertex or triangle. Okay. Right, so we're going to need to output a normal. And we're also going to need to output a position. And this is something where the interpolation will actually be useful. So we have positions for all of our vertices already right here. We also want the position in the world of each sort of pixel of the surface of the triangle. So we need to output a value for that as well, because that will affect our lighting, right? The amount of light that a pixel gets will differ as you move down some surface at an angle to the light. So to get the fragment position, this needs a type. These are both vec3s, 3-dimensional vectors. So it's going to be a vec3. We take the model matrix. Right, that tells us that gives us the information about where the thing is located in the world. And that's all we want, is a position in the world, not a position on the screen. All right, we multiply that by the position of the vertex. And that's it. And then since we have this separately, we don't need this times model here anymore. We can yank that out, save ourselves some work, because that is just the fragment position, right? So the GL position is calculating where things are on the screen, because it's getting multiplied by the view and the projection. So the fragment position is just the model part of that to get the position in the world for that vertex. And then texture coordinate remains the same. Okay, and I think that is it for the vertex shader. Yeah. Any questions so far? So I want to move over to the quad texture frag, or fragment shader. All right, so we've got our texture. Got our frag color, texture coordinate. So we're going to take in the normal and fragment positions. Those are coming from our vertex shader, but remember they'll be interpolated. So fragment position will not be the same for every position along the triangle. And I think that's it. No. We need, we're going to need to provide more things than just a texture. We need a position for our light. And if you wanted multiple lights, this would need to be an array of lights. We're going to start with just one. So the light is going to be at some position. And our light's going to have some color. This also represents the brightness. And that's it. Light position and color. I think we now have all the things we need to do some stuff. Okay, so we're going to keep our ambient light like this for now. We could make it one of the things that we pass in, but we'll just keep it hard-coded for now. And this will be our ambient. So we can play with like turning that on and off to see how it looks different. And this will be our, now we're going to calculate the diffuse light. Okay, so actually, we don't need to do that here. So let's do one more step in our GoGL helper library. Let's make sure that these are normalized. Right, remember normalizing just makes the length of the vector 1.0. Doesn't change which way it points, just makes the length 1.0. So back to fragment shader. Okay, so we got our normal. So light direction. So we want to get the direction of the light, which is a calculation involving the light position and the fragment position, right? Which way is the arrow going from the light source to that pixel on the surface? So we're going to take the light position minus the fragment position. And then again, we only care about the direction, not the distance, at least for now. You could attenuate the light by distance if you wanted to. So we're going to normalize that. And shaders are awesome, so normalize is built in. A lot of people don't like the shader languages, but I kind of love them. They have all these handy vector things built in, and vectors are what you're always doing, so I like it. Okay, so now you want to figure out kind of what the angle of attack is of your light. So if you have, why isn't erase working? Doesn't work with the mouse. All right. So if you have some surface and some light, and your surface has, this normal, and you've got some direction to the light. So this point right here on your surface, the direction of the light and the direction of the normal are the same, right? They're in line. So the light's going to be really bright. This point down here, the normal is like this, the direction to the light's like this. These are different, and so it's going to be less bright. So we want to calculate the difference between those directions, basically. So you can do that with a dot product. We did cross product earlier to get the normals. Now we're doing a dot product. Highly recommend, kind of, if you're wanting to get into 3D graphics, studying that kind of math a lot. I have to go look it up every time I do it. If you just know it, you will be better. So we're gonna get the diffuseness of the thing. So we take the dot of the normal. That's the way the surface is pointing, and the light direction. Now, A problem with this calculation is if the angle is, if the difference is more than 90 degrees, so, right, if you're a surface down here, and like the direction's totally, or sorry, like say you're, it's hard to represent in 2D, but if you go like beyond being out of the light, you'll get negative light values, right? You might get like -5. And you don't want to represent that unless you want to do some like crazy artistic thing. You just want it to be dark, right? So if you get beyond 90 degrees, you just want it to be 0. So you want the maximum of what this dot product is, or 0.0, right? That prevents it from going, it just prevents it from going negative. And then so your diffuse light value is the diff we calculated times the light color. All right, this is sort of like a magnitude, and this is your base light color. So you multiply to reduce or increase based on the diff. And then this becomes not just ambient light times your texture, but also the diffuse light times your texture. And I think that's it. So we have a few potential bugs here, so let's see if it works. Failed to compile shader, failed to compile shader. Which one? 25? Okay, so let's make this just a vec3. We're not doing alpha. Maybe that's it. Oh. Maybe we need to do this. Cast not allowed. Oh, too many parens. Okay, there we go. It's running. Oh, we haven't sent anything. We have not set these two uniforms. So let's do that. So remember, uniforms are things we have to set in our code. So are we setting? Yeah, so you see here we're setting projection and view. Do our shader programs have, where's GoGL? Does shader have a set vec3 yet? Set float, set map4. Nope, so let's make it. So the receiver on shaders, set vec3, and our vector 32 vec3. So we get the C version of our name and add the null terminator. And we get the location. It's the exact same code. And then I think we can do the same trick where we say our v3 is equal to an array of 3 float 32s. So happy with that? Yep. And then geom uniform 3FV. Let me check. There's many kinds of uniforms. Let's see. Yeah, 3FV. And so we give it the location, doing just one vector 3, and the address of v3 of 0, the address of the first element of the array. Okay, so now we can set three-dimensional vectors on our shaders. And remember, we need to set light position and light color. So where is I will use one of these positions slightly modified. So we're going to shader program.set vec3. That will be our light, what do we call it? Light POS. And let's make this like -8. And we also need our light color. And let's just start out nice and simple with a white light. All right, is that all we need? Oh, one more thing. So remember we added a third, a trim pointer. And that's going to be our normal. And we're going to need to return the normal. We're not returning the normal yet. So that's going to be our normal coming in from our vertex and trim pointer. And we'll need to return it. Why did that even run before? The GLSL compiler is not very picky. Okay, we see some things happening. So we see that we put the light kind of up near that top cube. Let's see if I can look around more. Let's try putting it in a different spot. Close this. Where are 3 cubes? Let's try putting it in front of everything. There we go. So now you can see the kind of lighting you might more be used to, right? So the light's kind of in front of the scene. So we see the lightly shaded side and the darkly shaded side. And let's play around now with our shader a little bit. Drag it over there. Uh-oh. There we go. Okay. So, right, this is with ambient light set to 0.3. So we can see, if we yank that out completely, then you can't see the sides that aren't lit at all, right? That's how it might look in an outer space. but not how it would look in a room or a forest or something, right? So that's the value of ambient light, is approximating that bouncing light you would get off other objects hitting things that wouldn't otherwise be lit. Then what other things can we play with? So we can change the color of the light, and that's part of our program, so we can't use our handy hot loading there. But we can, where are we setting it? Oh yeah, right here. Right, so we can make a red light. And then our multiplication lights it up red. And so here you notice that the ambient light is a different color than the diffuse light, which you can do if you want, but typically you want to make them the same. So what we can do is make the ambient light something you pass in to the shader. You can do this any way you want, right? There's no like right way to do lighting. They're all just approximations of reality, so you can do whatever you want. So let's do uniform ambient color. We'll just call it ambient light. So we can take this out of there completely. Ambient light's still there, but now we're going to pass it in from our code, right? So we're going to do so now, since our light color is red, we maybe just want to do a darker red so it matches. I think that should be all we need. There we go. It's pretty dark. I'll make it 0.4 so it's a little more obvious on stream. You never know what things look like when they're compressed on a stream. So yeah. And that makes a little bit more sense in those cases to have them match. Right, and you could also just make another approach you could do if you don't want to bother. If you're never going to have them be different colors, right, you can take that out. Take ambient light out here. And you just say vec3 ambient equals your light color times 0.3, for instance, right? You just dim it down, and then that's your ambient. And you get the same effect. You just don't have to type that code anymore if you don't need it. All right. So that is basics of lighting. There are other types of light you can add. For instance, there are specular lighting. So when you see like a shiny object that a light shines on, you'll see a bright spot of the light reflecting off of it. So we might do that next episode. And you can also just sort of make up your own things. You can make the light react on the surface any way you can imagine or want. But this is the basics. This is how it starts. Any questions so far about tonight's stream? Nope. Here we go. Questions. Okay, so my keyboard is a quick-fire, rapid gaming-coolermaster.com. Cooler Master, I guess, is the brand. Yeah, it's a clacky keyboard. I like it. 10 keyless. Theo Marist asks, is Go any good for games? What makes it special? Go is good for games in some ways. Some good things about it are the garbage collector is very low latency, which is different than the way Java and C# are optimized. They're optimized for throughput, which is doing the most garbage collection as they can, per hour, but they don't minimize pause times. Go tries to minimize pause times, which is very good for games. So that's a very good thing. Another good thing about Go for games is that it compiles to native executables, so you don't have JIT warm up, and it's easier to distribute your games. If you compile a game for a platform, you can just give someone the exe and your assets, and you're done. You don't have to worry about installing the proper .NET runtime or Java runtime for your game to work properly. Some bad things about Go for games are the interaction with C is not as fast as in some other garbage collected languages. Like the overhead for talking to C from C# and Java is a little less. In Go, it's a little more. Whether that matters or not just depends on what you're doing. Like if you're doing an OpenGL 3D game, you're not actually making a lot of calls to C per frame most of the time. If you're doing something special that requires that, then Go could be problematic for you. The biggest downside to Go for games is there's not much of an ecosystem for it. It's a language that Google kind of made for doing command line and behind the scenes server side stuff. So it's not got a lot of ecosystem around it. There's not a big engine like Unity or Unreal that use Go. There's not big frameworks like MonoGame that use Go. So if you do make a game, you either have to get C bindings to popular C libraries or do things from scratch. So if your approach is to do things from scratch anyway, Go can be pretty good. If your approach is not to do things from scratch, then you're probably better off with something like Unity, Unreal, MonoGame. libgdx is a popular framework for Java. So yeah, now I would say what makes Go special is compiling to native EXEs in a garbage collected language, which is rare today for some reason. C# and Java like to have these runtimes and JIT things. I don't like that, but they all perform similarly overall. So you should really just use whatever language you like best because it doesn't matter very much. Any other questions about life or the universe or previous streams? If you're young and want to be a AAA game developer one day, you should learn C++ for sure. But if you just want to make an indie game, you can use any language unless your game design happens to have crazy performance requirements. Then you'll need to do some C++ or C as well. All right, looks like no more questions. So good night, everybody. The lighting was cool. I enjoyed it. Next episode, we could do more lighting. We could add specular lighting. Or we could do model loading. There's a library called Asset Importer that we could use, and you can load complicated 3D models. So we'll do one of those things. Theo Maris asks, what game am I working on now? So my day job is not games, but I do have hobby games I'm working on. I can show one real quick. It's loosely based on the Evolving Pictures project we did on stream a few episodes back. I'm doing it in C++ because there are some crazy performance needs I have where I have to use SIMD intrinsics, which look like this stuff, where you can do 8 math operations at once. You can see divisions and multiplies and stuff. And it's hard for me. I don't do C or C++ all the time, so my code's a mess. But it's basically based on the Evolving Pictures project. Oh, that's a debug build. That's going to be slow. And it involves kind of, you're an explorer in space researching what these things are that you find in space. So you kind of explore. You can find these things. You can buy things to research them. It's like we can get a big view. So I don't want to give too much away because it's kind of a game about figuring out what's going on. But that's what I've been working on in my spare time. We'll see how it goes. And I definitely run into bugs that take a lot of time to figure out a lot because I'm not experienced at C++. So there's definitely times I wish I was using Go or C# instead, but I really need SIMD intrinsics, which are hard to do in Go and impossible to do completely in C#. I don't think you can do them completely in Go either. All right, good night, everybody.